I'm going to go on mute here, and we'll see you all back here in about 5 minutes or so. That's great. Can you see that, David? Everyone, David, it's your co-host. You have to tell me what you can and can't see here.
Yep.
Okay, great. I'm going to go to full screen. This is a PDF again, but I now have the ability to do full screen.
Well, it's a shame you can't see the gallery.
I'm sorry?
It's a shame you can't see the gallery.
I can see the gallery now, but I can't get out all the controls.
Okay.
So what is it? Does it look okay now? Are we ready to go?
Yeah, look good. Part 1.
Okay, yeah, part 1 and 2 are both tonight. So, but they're both short. The reason is because when you make these things large, they start misbehaving. So, okay, are you recording?
Yes, I think I am.
All right, I'm counting on you. Well, I want to take a moment here to welcome everyone from both Chapter 21 and any other chapters outside of 21. Members of other chapters are always welcome to our presentations, and we like to both encourage it and make you feel as welcome as possible. And you know, we usually, I mean, people are welcome to ask questions, but for some reason we haven't had a lot of questions over the course of the last few presentations, and that's okay. And you know, when I save up questions till the end, that's okay too. But let me just say thank you all for joining for our presentation tonight. So the title of our presentation is The Hammond Bike Harness Restoration. Now, I've always been somewhat fascinated with Hammonds in general, and they have an interesting history we're going to get into in a few minutes here, but it's interesting that in such a very short time, Hammond managed to proliferate such a vast number of clocks, and you almost can't help but run into these things. So that's kind of, to me, what makes these interesting. They're very charming clocks. The bike harness clocks are are unusually interesting. The cases are unusual. The clocks are much more robust than their other models. They have a variety of different packaging. And they have a really great power outage feature. They keep running for 30 minutes after a power outage occurs. So you don't see as many of the bike harness clocks as some of the others, as their standard synchronous clocks that are they're so-called spin to start clocks. They, I suspect, are rare because they're not easy to repair, and as a result, they end up going in the trash, which is a very terrible thing because they're very repairable. The things you tend to see are broken fiber wheels and, I mean, catastrophically worn phenolic plates, and we'll talk about what all that means. Yeah, they can be tricky to restore, but I mean, once you see what we're presenting tonight, you might just say, hey, this isn't all that bad. You know, you see various posts on the NAWC boards about, you know, things related to these clocks that often aren't true. And maybe we'll take the time tonight to demystify and debunk some of those things and show you that you really can repair these clocks. There's a half dozen or so general issues you run across, and we're going to cover them all. And you're going to get to see what goes into this. And one of the cool things about doing these presentations is some of the material that you'll pick up here, the material is useful in other kind of applications and other repair and restoration activities that you might do. So here's what our agenda is going to be like. As I said, we're going to do a Hammond history, talk about what bike harness means, what goes wrong, skill level needed to do the repair. It's probably not the clock you want to pick if you've never done a clock repair before. You know, try something else first and then get used to work your way up to working on a clock like this. All the way up to, we're going to even talk a little bit about fabricating fiber wheels, which we've kind of alluded to in the past, but we're going to try to cover it tonight as, rather briefly, but we'll pick up the key highlights and give you a good idea how to do it. So as I said, medium to advanced skill, you're going to have to make parts. There's no avoiding it with these things. But one of the more important things that I should probably have listed first is the safety aspects of working on electric clocks. If you don't feel comfortable, don't play with electric clocks, because there's a danger, especially if you plug them into the wall and you start tinkering with them. You could cause fires, you can cause a heck of a lot of fireworks, or you could get a pretty nasty shock, or goodness help us, you could even be electrocuted if you're not careful. So, if you're not comfortable working with electric clocks, don't play with these things. I'm going to tell you that right now. But I mean, with a few interesting lessons, you could become comfortable with them. But don't go there unless you think you could do this and handle that aspect of it safely. Of course, you're going to need lathe skills like always, making rivets, bearings, cleaning up pivots. We're going to do some gear cutting on the mill. And, of course, doing safe, solid, clean soldering is important to getting the safe connections from the line cord into these clocks too. So here's a little bit of a history. I'm going to tell you, this is very close to what is documented on the Wikipedia site. Lawrence Hammond, founder in 1928. The production clocks at Hammond discontinued in 1941. So do the math. That's not a lot of years. And it's amazing to me that they created as many clocks as they did. So their original idea for this thing was, obviously modeled after Henry Warren's invention of the synchronous motor, which locks to the line frequency. And since Henry Warren dealt with all the issues of keeping the line frequency synchronized exactly so you have the same number of pulses every 24 hours, he took care of all that. So as a result, if you had built a synchronous clock, it would keep good time. Without Henry Warren's invention that basically governed the speed of the generators, that wouldn't have been possible. So yeah, they did a synchronous motor tied to power line, but in order to be able to avoid the Henry Warren patents, was not self-starting. I mean, and then they sold that as a feature. That is, if the power line failed, you would know it and your clock wouldn't keep the wrong time. It would just be sitting there dead and you'd know that you needed to go seek out the proper time. So they kind of turned Henry Warren's self-starting thing into kind of a downside, until Henry Warren started putting the little red flags on little circles on his dials to indicate that a power failure had occurred. But in any case, they produced hundreds of different models of clocks over that short time. But somewhere around 1932, it turns out that their patents, that Hammond's patents, were proven invalid because an earlier German patent had been issued using the same methodology. And it turned out that the company kind of struggled financially after that until Lawrence Hammond decided to move on to producing organs. And that then, morphed the company into the Hammond Instruments Company. So then the production of clocks discontinued right before the war. And if you want a little bit more detail than this, you might want to check out a couple of these references. One of the things that's starting to become somewhat illuminating for me is the fact that I'm seeing more and more watching clock bulletins focusing on electric clocks. Over the course of the last year, it seems like more and more articles on electrics. And here's an example. The June 2020 just happened recently. Hammond Company of Canada Limited. Really good article by Alan Simmons, shows various models produced in Canada. Great article if you're a Hammond buff. Organhouse.com is another good one. And then Clock History, of course. Our good friend there continues to publish interesting stories and histories. Bill Stoddard, really good, super good historian, doing a good job with his website if you need a reference on all different models of small clocks. Generally, he has a whole section in there on larger master clocks too, but he's generally focused on alarms and small electrics and things like that. So here's an article right from his website, Bill's Clockworks website, the advertising for the Hammond Bicronus electric, and you can see the movement there, rather interesting, kind of a almost a three triple decker movement, if you will, and advertising that the clock will continue to keep time when current is interrupted. And it does that because it has a mainspring in it, and the clock, the normal function of the clock is to wind that mainspring. When the power is discontinued, the mainspring takes over and keeps the clock running in kind of the same speed that it operated previously to that. So now it's not quite that perfect, but it's pretty good. So that's that's a little article that came up. Here's some examples. And I mean, some of you probably own clocks that are like this. These are both Hammond Bicronus. These are in my collection, actually. It says eBay, but I saw the same clock on eBay. Anyway, so here are the kind of the major failure points. The phenolic bearing plates, the pivots don't rest, for the most part, I should say. The pivots in the main wheel trains don't rest in brass. They rest in these bearing plates that are made out of basically phenolic material. And they're really hard to just rebush. The only way I've found to really service them is replace them. And the way you replace them is you make new ones. Not very difficult, but it's just any shortcut to this, unfortunately. Once they wear out, there's just no real practical way to get a good bushing in there. So the other issue that you run across with these clocks is the phenolic wheels. They break, the teeth break. And if you get one that happens to have good teeth, you know, well, just wait a few months after you put it back in the service, those teeth will come off. They get really brittle. The material just the resin seems to get brittle with age, and they just kind of fall apart eventually. So the other aspect of these things is none of the wheels are single wheels. They're all tandems with concentric bearings, and that kind of presents some interesting challenges getting those apart. And then, of course, you have the usual worn and scored pivots and plate bushings and things. The mainsprings get filthy on these things, and they have to be cleaned. The barrels are not easy to get into, but it can be done. And of course, the cords get absolutely ratty, and you do not want to be using one of these clocks with cords that are unsafe. So that's really important. And I'll give you a reference at the end of where you can buy some really nice rayon covered cords that look like the originals, but are really well made. So here is our, I would like to say, subject clock today. And as you can see, they kind of come in pretty dirty, and often they're crumbled and the cords are falling apart, and the once cloth covered now is dust covered, and they tend to be in pretty bad shape. And this is what they look like as found. Here's another close-up view. And you can start to see how I've been describing these tandem wheels. As you can see, every wheel in the train is stacked on top of itself. And one of the deckers, if you will, one of the layers is for the side that winds the mainspring, and the other is for the side that times and runs the clock synchronous to the line. So when it's fully wound, those two are running at the same speed. When it's unwound, the side that winds is absolutely cooking to try to get that mainspring wound up. So what I did here was I took the movement after it was all repaired, and I put it together without the coil and field assembly, because with that field assembly in there, it's really hard to see things in this clock. So here you can see what's going on a little bit better. And here is the heart of this thing is the rotors that run it. And on top here, there's a toothed wheel, and that wheel is the synchronous wheel. That one engages with the power line via the field assembly, which is also toothed. So in such a way that, you know, each pole, you move from one pole to the next every cycle of the mains. And in that way, it locks the speed of that train to the line frequency. But down here, we have the winding rotor. Now it's a disc. Well, what does that mean? Well, it means it's got one pole, basically. So it's going to try to run at 3,600 RPM, but it can't, because there's friction and then there's back pressure from the spring. But it really cooks when it's starting to wind up. It takes off and goes pretty quickly, but eventually the load of the spring slows it down and it loses synchronism pretty quickly. And then and the speed is basically governed by how much, what remaining force it can apply to that train as that spring gets stronger and stronger and pushes back. So, and in here you can see there's the wind fiber wheel, which ties directly to this winding rotor disc. And then there's the timing fiber wheel, which ties to this pinion is fastened tightly to the shaft, which runs up to the timing rotor, as you can see. And this one is a bearing so that it can ride freely on that same shaft, and thus tandem wheels. So that's how this section of the clock actually works. If you back off a little from it now, you can see some of the other details here. Here's where we had zoomed in earlier with the two rotors and the two fiber wheels. And you can see we talked about these bearing plates. There's 3 of them in the clock, one on this layer, one here, and another one on the top layer. The mainspring barrel is here. The barrel itself is actually in series that provides the drive to the motion works via the second hand, and that's on the top layer down here, which we don't show yet, but we will. And here is the intermediate wheel of that, which is at this point a little hard to see, but you get the idea. And then you can see the 4th tandem wheel here, the 3rd tandem wheel you can see on this view. And you can see that you have the rotor as number 1, number 1 tandem. Number 2 is the fibers. That's your 2nd set of tandems. 3rd one here. 4th one you can't see in this view, but you can see in this view, there's the 4th tandem wheel. And then here's the 5th tandem wheel, and then the mainspring barrel. Now, the other interesting feature here is the backstop ratchet, which what happens is when the power fails, this whole thing wants to back off and take off in the backwards direction. But this little ratchet here, it's one of those silent ratchets that just kind of runs along peacefully along the ratchet wheel. But when you try to run it backwards, it kicks in and it stops that from happening. And then, the drive then goes backwards through this wheel to the all the way back up the train to the rotor, and keeps the rotor moving while there's no power there. And by the way, it's pretty much the same speed for reasons we'll get into in a few minutes. So that's the general nature of how this movement actually works. And when you first look at these things, if you get one that you found at an auction or something, you take it apart, you'll find that, oh my goodness, the oil in between these wheels are supposed to move freely with respect to each other, each one of these tandem wheels. Well, you'll often find that they don't, because the dried grease, lubricant, and the little particles of worn out metal all kind of bind together and turn into a super glue that keeps those wheels pretty much locked together. Well, in that case, you're not going to get anything to happen when the power fails. It's not going to be bicronous anymore. It's just going to be a synchronous clock if you're lucky enough to have enough of it intact that it will keep running. So that's one of the things you will find, is these things tend to seize up that way. The tandem wheels are a source of headaches. So my recommendation, even though you could always refer back to these pictures, is take pictures during disassembly. Make sure the mainspring has been let down before you take them apart. And sometimes that can be challenging if you've got seized up wheels and they're seized up with the mainspring fully wound. It can happen. And so you have to be really careful with that, because otherwise you're going to end up with a bunch of pretty much beat up wheels and teeth from that thing releasing suddenly. I'd recommend to start off, you go use NAWCC21 for all the tandem wheels and plates. Even though you may very well be redoing all those fiber plates, you don't know until you get it apart where you're going to have the work. And so if there's no wear, you don't want to be using an ammoniated cleaner on that material, because it doesn't like it. The ammoniated cleaner and phenolic don't go together. So, and after that, do a naphtha rinse. And any of the brass and steel parts can be clearly cleaned in the ammoniated. Now, why do I say to use the NAWCC21 on the tandem wheels? They're all brass and steel. Well, for a very simple reason. You don't want to, if they're in good enough shape that you don't have to disassemble them, you don't want to get water into those bearings. You want to keep a waterless material that'll evaporate out in there so that you don't have problems later with rust. So here's the disassembly, and you'll notice the first thing we do here is we took the top plate off. We didn't even take the rotor off the front plate. We left it on, or back plate. We took the whole thing apart together as an assembly. And this is all that's left. If you look at this thing, not a whole lot from the top. It kind of doesn't, if you look at this thing layer by layer, each layer is fairly simple in these clocks. So here's the rear plate view. We take it removed. And then you can see the upper train here with that plate removed from another angle. Now we go to this next step, which is to remove the motion works. And really it's as simple as 3 screws and you're out. Here's the motion works, and you just literally can lift these right out of the movement without any issues. There's nothing staked quietly behind plates that holds anything together. It comes apart pretty straightforwardly. And in the third step, we take the top plate, the front plate off, and you'll see the mainspring barrel, which will be a lot of fun to pry apart. I actually won't say too much about that. And what I usually do is just take a screwdriver and go around it, a sharp screwdriver, like a watch screwdriver, and go around it little by little, and eventually you can pry that barrel off. Takes a little patience, and it's a little slow, but you get there. And note this center shaft. This is an important element. There's a little fiber washer on top of that, that center shaft. Underneath, there's a spring that's trying to put pressure on this shaft so that the second hand doesn't have, well, anywhere near anyway, as much free play in it or backlash. As you can see, these are pretty coarse wheels. And this, as I said, the mainspring barrel actually drives the second hand in this movement. So there's a lot of backlash there. And so they put a spring behind this, which isn't shown, but there's a spring back there you don't want to lose. And you need to put that back together the same way. So, and there's sometimes a little bit of wear here. We can actually replace that, make a little phenolic washer to replace if it's deteriorated or seriously worn. So that's what that looks like. And here we want to take apart, we want to remove the coil in the field assembly. You'll note that there's a couple of spacer washers in here. The short one is in the back, not by the coil, and the longer one is up on this end. And you could say you take those 4 nuts and bolts out, take the spacers out, and out it comes. Now, usually what I'll do is just blow dust off the coil and field. Don't immerse it in anything, for goodness sakes. These coils are unique. Hammond used to make these things and soaked them, impregnated them with wax. And as they warm up, sometimes that wax starts to ooze out, drip out. They tend to be okay, these things, because there's a separate terminal board holding together the wires that attach to the coil. They don't tend to be damaged. So you often can reuse the coils as is. And I'm going to assume for this restoration that the coil is fine, as they usually are. Here's the tandem wheel situation. All these things are held together. You can see here, this wheel is fashioned to an arbor. This wheel is riding free on the arbor. And this is nothing more than, in this case, it's steel. I'm not sure exactly why they use steel. They could have used brass just as easily. But this often needs to be either filed away or turned off to get that out of there so that this assembly can come apart. And what I usually do is I'll mount this in the watchmaker's lathe right here on this shaft and work away with a parting tool and just sort of chisel away at this thing until it's thin enough to where it loses its strength and can be easily pulled off with a pair of pliers. They're easy to make new one. It's easy to make a new one. It's no big loss. Take good measurements before you do what I just told you to do so that you can replace it later. So, and one of the things that you're going to find as you go through these is even the bearings inside of these fiber wheels, these free running fiber, these things wear out too, and they wear out seriously bad sometimes. So let's talk about fiber wheels. As I said earlier, they often come to you pretty badly broken up. This particular clock was only missing 2 teeth. Usually I see these things come in, an entire half of the wheel is missing teeth. Now, how does that happen? Well, I'm not sure. And you'll sometimes have one fiber wheel that's good, but if you're going to make one, make them both. mean, you're going to be on the tool anyway. You're going to probably make 6 at a time. Why mess around? Just replace them both. They will eventually break. I can tell you from experience that sometimes in some of the lighter weight, non-bicronous Hammond clocks, the wheels will last a little longer because there's really not a whole lot of force on them except the starting torque when somebody goes to spin start them. But even there, you can sometimes run into trouble with the teeth breaking off, kind of in latent fashion. So let's talk about how you make these things. Starting with the raw material. You're going to need to get some phenolic sheet, and I don't care what color you get. There are standard sizes available from 032 and up, but all we're going to need here is 032 and 063 for this little project. Natural linen LE, I think, works the best. It's got the finest mesh. It even advertises as being suitable for small machines and gears and things. It's supposed to be an electrical grade, but the mesh is fantastic on it. It's very fine, and it works really well in making small parts. And it's really super easy to cut and machine. And here's a link to where you can find it. And Professional Plastics has a whole array of different materials, and they'll sell to anybody. And they can sell you 12 by 12 sheets, which will last you half a lifetime. So you can sometimes get small quantities of this stuff on eBay and Amazon, but I don't know. I bought some on eBay once, and they claimed it to be linen LE, and the mesh was like, screen door kind of mesh. It was very coarse, and I wasn't satisfied that was going to do the job. So I went back to Professional Plastics. Now, that's not to say, I mean, the more coarse stuff could be used for other things too, but kind of not. I'd prefer not to use it for this. I like having that fine mesh and that reinforcement in there. Now, sometimes when I'm making fiber wheel replacements and the diameters are very small, I'll actually cut it directly out of acetyl or Delrin rod for small diameters. It's just easier to cut. You can make a bunch of them all at once, and you're limited by how much of that piece you can part out, how many you can part out of a rod, for example, if you cut it into a 3/4 inch rod. So, but for the purposes of this project, we're going to use the same material that was used originally with these clocks, which is the phenolic sheet. So the first thing we want to do is disassemble. You'll see the side view here. You can see in both views actually that we're held together by a little riveting action that went on in the manufacture, and we have to get that out of there. So no kidding, we're going to put it in the lathe, and just like you would turn down the rivet on a balance staff to remove it from the balance wheel. It's similar to what we're going to do here. We're just going to take that rivet out a little bit, and once it's just right, you can put it in your put it into a whatever form of, you can make one yourself, or you can buy an anvil with holes in it and drive that right out. There's a pinion behind there. You want to put it in a hole that clears the pinion, and you'll just drive it out. It pops right out. Simplest thing. And now you're going to make a measurement. Now, of course, this was the other wheel, I must say, as a kind of parenthetically, a sidebar. The other wheel didn't come apart quite as easily. And you'll see why as we get back to the reassembly there, that there was really no way to drive off that bearing raceway. And so it kind of came apart in pieces. So here's the specs on our wheel. OD 1.275, ID. I start out with a 1/8 inch hole because I can punch it and it's straightforward. And because I already have an arbor that's designed to handle the 1/8, so it's real convenient. Thickness, of course, 0.032 on these. They're very thin. 60 teeth. We're going to talk more about cutters, but this was the cutter I selected, and we'll get into more of that later. The depth of cut on that cutter was 0.47, and these two go together really carefully. So if you wanted to make these wheels and you wanted to buy this cutter from PP Thornton, there's your formula. It works real well. So the first thing you do is you make up the blanks. You start with the material, put a little bit of layout dye on it. And here I've prepared 6 wheel blanks, dimpled the center, used a compass to scribe. And I cut a little oversized at this point, since we're going to turn a stack of 6 of these blanks in the lathe later. And once I get these out of here, I'm going to punch with an 1/8 inch with one of those little hand punches. And then we'll rough out the circle on a bandsaw or something similar to that. I mean, you could use whatever you want. You could use a jeweler's saw. You could use a DeWalt scrolling saw, whatever you choose. This stuff cuts super easy. It's fast and it's clean. And unlike fiber material, it doesn't chew the blade up. So it has that going for it. Now you're going to need a mounting arbor. You're going to need to make the OD of the arbor so that the root of the teeth is just under that size. And so you're going to also need to have a hole and a screw. In this case, I believe I used a 440 screw. I did something interesting here, which was I drilled a hole through the center of the screw so that I could spot center when I set up the cutter. And that kind of worked out actually better than I thought it was, considering it's a screw. So, but these are arbors that take you no time to make. You can make these in 5 minutes on a Shoreline lathe, and you're in business, and you can mount these wheels up and cut as many wheels as you want, within reason, of course. So let's talk about gear tooth shapes really quickly. Now, there's a lot of geometry and math behind this. We're not going to cover it all. The important thing here is to know that is to be able to recognize two different tooth shapes in your work. One is involute and the other is cycloidal. Now, the key with involute, as you can see on the right here, and you look at the shape of those teeth, and you can see that they're dramatically different than what you see with cycloidal teeth. And the difference is that the geometries work out much better for wheels driving pinions in the case of cycloidal, but in the case of involute, the geometries are designed so that you get efficiency with pinions driving wheels. So, and there's a big difference there. So in most horological work, the wheels are driving pinions. As you think about it, we're gearing up. We're decreasing torque as we work our way down to the escape wheel, for example. And so in those situations, cycloidal gearing gives you a much smoother, more rolling action effect than involute will. In fact, in some cases, you can't turn a cycloidal around and use it to take the pinion and use it to drive a large wheel. It just doesn't work efficiently. And the same thing goes with involute, vice versa apply there too. So there's the differences. In this case, we have a pinion driving a wheel. So our tooth shape's actually more on the cycloidal, on the involute side, which as I said, for horological applications, is unusual. In fact, that's the way the entire train, this clock is designed. You know, pinions are driving wheels all the way up the chain on it. So, but what kind of cutters we have? What kind of cutters are we going to use here? Obviously, if you make your own fly cutter, you make any shape you want because you're going to make the cutter fit the tooth. And a cycloidal cutter can sometimes be adapted to involute if you're careful about matching up the shape of the tooth and the geometry. You get very, very close. It's not exact, but it's close enough often that the differences are not going to cause any issues. And the way you get it to work is you don't cut as deep. Usually when you take a cycloidal cutter, you cut all the way to the tooth tip. But in the case of using it to create an involute, you don't cut all the way to the tooth tip, and get a little bit closer to an involute kind of a shape. So you can also just go out and buy involute cutters, but man, that's tough because it's really tough to purchase cutters from specs. And really the only true way to do it is to match up the cutter to the tooth form that you have. And that's really hard to do. It's a buy and try kind of a effort. It gets to be expensive if you're buying these. You're trying to, kind of find one cutter. So, and of course, many of the common involute cutters are way too big for the miniature work we do. So, anyway, here's some examples of horological cutters. Here's the PP Thornton, similar to what we're going to use. And you can literally go to their website and buy these cutters one-off, direct from England. These days, they actually have a real nice setup now. There's another site called Timekeeper's Workbench that makes single tooth cutters. They're okay. They do all right. You have to run them high speed. And again, you have to match them up to the tooth form to get what you want. Or you can make a custom cutter and holder, and you make any form you want. Match it up to anything. So there's your choices. Here's a close-up of the fly cutter. Sorry, the picture's a little blurry, but you can get the idea here. You have a little set screw. You have this device, which is cut from a piece of, well, even 12L14 steel would work for this. because you don't really need to harden it. It's plenty hard enough to do the job on a meek little, you know, fiber wheel or even a brass wheel. You don't want to cut steel with these. You want, if you're going to cut steel, you're going to make steel pinions, you want to use the Thornton cutters, because you just need a smooth cut and something that'll take off small amounts of metal at a time. So here's a close-up of the cutter. You can see it's cut. We've created the shape of the tooth, and then we mount this in the cutter. And the idea behind all this is to cut one tooth. You're cutting the space out between two teeth. So you're creating a half a tooth on both sides. And then you index from one tooth to the next, to the next, to the next, all the way around. So here's the fly cutter detail if you want to look it up later. We're not going to go through this now. For the fly cutter material, you can use drill blanks. 1/8-inch drill blanks works fantastic. Now, you know, I used to use tool steel, 01 tool steel annealed and then harden it later. But here's the thing. I'd find myself using grind wheels to you know, get the form I wanted out of the tool steel, the annealed tool steel. So I thought, well, I'm going to use grinding wheels. I might as well just use the high-speed steel and skip a step of hardening the material. And it's worked great. I've never gone back. I've stuck with this. It works out well. You can do fine cuts with diamond files or stone. It's just, you're not removing a lot of metal. Once you get the initial grind in there, you're not removing much metal. So it's not a terribly, it's probably a 15-20 minute job to make a cutter out of this material once you get the hang of it. And here you can see the process. You start by, this is literally a Dremel tool with a grinding wheel, and you grind away it to get the shape to what you want. And as you get closer and closer, you'll start to see, you need to look at this under a loop in order to make sure you've got that shape right. Once you get it, you go ahead and grind flat to center, and now you've created your cutter. And then to optimize the efficiency of the cutter, you do a back cut at the tip and a back cut at the cycloid too. So that as the cutter is passing through the material, it doesn't jam up and create friction there and heat, which is an enemy to any cutter. Here's an example of a close inspection of the cutter, and you can see here, well, we're not quite there yet, although, as you know, when you have a worn wheel, you have to extrapolate a little. So since it's symmetrical geometry, you use this side to determine if your shape is right, which here it was not quite right yet. So there was more work. But the point of this illustration is this is how you see where you need to work the tool to get it to where you need it. So for us, we're going to use an M0.5-10T pinion cutter from PP Thornton. Determined that this works fantastic. So if you want a shortcut, just use this. Go out and get this part off their website and use it. It's as simple as that. Save yourself the trouble of fooling around. And making the arbor is a piece of cake. This is a simple cutter holder for mills from the Shoreline catalog, and they're not expensive. And you can make this out of brass because you're not cutting heavy material here. Nothing is going to be a problem with the amount of light work that we're going to do with cutting these fiber wheels. And for that matter, even brass wheels would not have a problem with this setup either. So now, how do we index? Well, you know, we're going to need a couple things. We're going to need the mount, some form of a fixture, some form of an indexer to the mill. If you want to use this middle form, or you want to use the CNC controlled indexer, you're going to need this Shoreline 3701 right angle attachment, or you could buy one of these or find one of these used, these little Huckabee, I call them Huckabee fixtures. And they're just basically index wheels. And for a wheel as simple as the one we're going to do here, an index, this device will actually work just fine, because 60 divides very evenly into 360, which is the number of degrees in a circle. And this is a piece of cake. This is a piece of cake from the indexing perspective. Any dividing wheel you find is going to have 60 teeth in it. And if you do it on an index wheel, you just have to index every 6 degrees. And if you don't want to have to sit down and figure all that out, then buy the automatic tool and it'll figure it all out for you. I started out literally in this order. I started doing wheels with the Huckabee, then found that I was getting into wheels that had funny counts. And so I needed to be able to create random counts. And then I needed to create Excel spreadsheets that gave me each step. And then that got to be hard. And then I eventually went to the CNC. So But there's some situations where I actually find myself going back to the manual approach here too sometimes. So they all work. It's just a matter of how much patience do you have and how long do you keep that patience after you've done a few wheels. So here what we're doing now is we're using we've got the setup, we've got the chuck with the arbor, literally that we just turned these wheels all to the same diameter on the lathe, and we take this chuck off the lathe and put it right onto the fixture here where we have the rotary table. And it's one of the wonderful things about the Shoreline system is you can do that. Whereas in other systems, that's just not possible. So that's what I love about using this system to make gears. So here you can see we've got the cutter installed and we've located center, even though this particular picture doesn't show my little pilot. It really does help to have that little pilot. Then we set the approximate depth. The first pass, usually when we're doing brass wheels, we cut a little at a time. But if I'm using a multi-tooth cutter and, fiber, I can literally cut the thing to full depth on one pass. So, and then we have to figure out our front clearance. We have to figure out where to return the y-axis when we are done with our tooth. So we need to clear it. And you can see here the clearance that we allow. And then look over here, we go the other way and full travel clearance. We want to get past, and this is actually a little further than it needs to be, but you want to get past the wheel so that when you're done with the cut, and you'll know it. I mean, as you're going through this thing, you can tell when you're done with the cut. You can hear it, you can feel it. And so now I put tape here so that I know where my start and end point is on the y-axis. I'm ready to go. And the next thing you know, we're up to tooth 60 on our mill, and we've basically cut all the teeth on our fiber wheel. And there you have it. We dismounted. We had 6 wheels, and here are 2 of them. They're all the same. There's no better or worse. They're all equivalent. And there you go. So now we're going to go on to part 2. And so let me know if we can you see this now, David? Can we see part 2 here? Can everyone see this? Can anyone see this?
Yes. Yeah, we can see it. Looks good.
Okay, great. Thank you. Okay, let's jump in here. So now we're going to mount the wheels. We're going to take care of the hub bearings on those wheels. We're going to do the phenolic plates. And then we're going to take care of the other problems we have with tandem wheels and other miscellaneous issues in the movement. So let's jump right in here. So in order to be able to find the center of the wheel that we've just cut, and that's really important because if you run this wheel and if it's off center, you're going to hear it. It's going to, on an electric clock, you're going to literally hear it just rumbling at you. So we've got to find dead center. In order to do that, we take a Shoreline faceplate, which comes with the lathe, and we mount a piece of wood to it. And I found that soft pine works. Hardwoods actually work too. Poplar works great. Pretty much any wood will work that I've run across, except maybe balsa or something super soft like that just won't hold together. So we go ahead and mount that on there. And in order to be able to get the wood on there, I've drilled through 3 extra holes in my 40070 so that I can run some wood screws in there, hold it good. And then you can see here what we did was we opened up this section of the wood with our boring tool, so it just accepts the wheel. And I mean just, it has to slide in. It cannot be forced. It has to just slide in, but yet have enough friction to hold it in place. And that's the hardest part of this whole thing, is getting this diameter just right so that happens. But you can see here, we've opened the holes until we have it just fitting on the arbors in both cases. And the key here is we want them to be snug, but we don't want them to be tight. If you make them tight, I'll tell you, these wheels will dish out so easy because any force on that center is going to cause the wheel to turn into a plate you can serve your steak on, and you just don't want that. So again, snug, but not tight. Okay, and then what we're going to do is here we have to make the hub, and we have two wheels here. We have, obviously, we have one that clears through the center shaft of the first, and the first that has to be mounted onto the hub of that center shaft. So we're going to start in this case with the wheel hub for and in this little raceway we have to create. It turns out that this little device actually holds the wheel on too, which is really convenient. So in order to do that, we bore out here, as you can see, from quarter inch stock. And then we do a little inside shoulder, which we need for the bearing that's going to be put into this. And then we part it off, and we're ready to go. It's not a very difficult part to make. It takes about 3 minutes. Very simple. And we may have made parts more complex than this in our lathe class. So, all right. So here, what we've got is the outside wheel, which carries the arbor that then carries the other fiber wheel that we just saw in the last picture. So what we do is in this case, we turn up a 0.35 OD washer, 20 thousandths thick part off brass. With, again, the inner hole has to be snug to that arbor, just fits, because then we're going to take this thing and we're going to take a punch and just lightly tap around the outside of this punch from all angles until we get this metal to spread around this, and then it ends up ultimately riveting that brass washer down to the wheel, which, since the wheel on the other side is supported by a pinion, you've locked it all together very tight and it holds very well. And that's it. You've just replaced the fiber wheel. So now let's talk about these hub bushings. We've got two sets of them. We've got a set in the rotor, and we've got a set in the second wheel here that we have to go back and address. So to start with, these things wear out. This is the same fiber material that's used everywhere in these clocks, and it's terrible. And you start getting down to these things, they are very small. I personally prefer engineering plastics to this stuff because it's just crumbly at this size. Now, I grant you probably could successfully make this bushing out of, just buy some of that same linen LE rod. You could buy a 1/4 inch rod and machine it down to the size, drill it. It'd probably work okay. But I kind of sort of fallen in love with this PEEK material. I love it because it's super stiff. It's twice as stiff as acetal, so it's a much better material to machine in these small kind of geometries. And what it also does is, by having a little more stiffness, it assures that when I drive that bush in, it's going to stay there. It's not going to be mushy and try to work its way out. So I've kind of gone to PEEK for these sorts of things. We'll talk about what PEEK is. It's not a cheap material, but in the sizes we want, no, it's not an issue. Cost is just not an issue. So here, what we're going to do is we're going to mount on the 4-jaw chuck. We're going to true up. This part has a little bit of a nub on the back, so it mounts in the lathe chuck really nicely. In fact, here I think I just mounted it. In one case, I mounted it in the chuck, but in both cases, I could have just used a collet, which I did here to get the underside. As you can see, there was a hub here that I could grab onto. Anyway, so I removed the material, and I true it up so it's nice and clean, so I'm ready to go ahead and put the bushing in later. And now we're ready for the PEEK bushing on both sides. And here's the PEEK material. It's a whitish material. It's not bad to machine. It machines well, but any of these plastics, the swerve tends to grab itself around the parts, so you're constantly pulling these little strands, these little hairs of material off of there. But it's not real difficult. When you finally got it down to the diameter where it'll just fit nicely into that hub, you part it off. Note the way I marked it here. I just took a typical Sharpie pen and made a mark around it and marked it with then I marked the Sharpie mark with calipers, with a set of digital calipers, so I knew where to part it off. And those who took the lathe class will recognize our handy dandy little part off tool here, which works better than absolutely anything else for this job. And this could have been done in the Shoreline if I wouldn't have started with a piece of 1/2 inch stock and had to work it down. You can buy this material in 1/4 inch or other sizes. So yeah, it's probably what you should do. So here we go with the little peak bushings installed, the center holes drilled, and I had to very, very lightly go ahead and just touch them with a broach to open them up. Not a problem. The bushings are thin. They're only about, did I put a number on that back there? I think they were about 40 thousandths. Yeah, they're only about 40 thousandths thick. So taking a broach to that is not a problem. And so there you have it. There's that side. And you have to do the other side too, the same way, same size. And then we go ahead and we just reassemble everything. And there's our two wheels here. We had to machine up that little brass bush to drive onto the shaft so that it holds everything together. And there you go. We got those all taken care of. Now we're going to turn our attention to this tandem wheel, which kind of was a little bit of a nightmare on this clock. So in order to do that, I need to get this pinion. I need to get it into my chuck. Well, the pinion's too big for any of maybe some of you folks have lathes that have larger collets, but I don't. And about the biggest I can go is about 320, and this is bigger than that. So what you do in those cases is you take a piece of stock brass and you drill it out to the size, exactly the size of the OD of this pinion. And then you add maybe 1 millimeter to it, and that's your OD. And you start out with a little ring, and then you just cut it with a jeweler saw, and then you can mount it right up in the lathe, preferably 4-jaw adjustable, so that you can adjust the run out on it. It's very important. You want this to be nice and clean, and you want everything running true. And then you go ahead and you draw out that center. Sometimes you need to use if you need to use a starting drill in order to be able to, centering drill in order to get this true again, you may have to do that. But generally they wear out relatively evenly. So it's a matter of enlarging the center hole so you can get the bushing in there. Here you make up the bushing. I use 544 bronze. The original was steel. I used 544 bronze. I don't think there's going to be any difference in performance there. I guess I could have turned it up out of steel if I wanted to, but here's the other interesting thing. The arbor was pretty much worn out. As you can see here, we had a pretty deep groove there. So I just bought some 0.7 3-inch drill blank and ground it down the size, and voila, I have a replacement arbor. And so, and of course I used the Alvord pole reamer because these are pretty deep. Look how deep that bushing is. You can't open that with a broach. So, and here we have our 4th tandem complete, running true and running without any rock. Before we repaired this thing rocked all over the place, like almost enough distance traveled to make up for the distance between the wheels. It was worn out. And that's what tends to happen when they do seize up. You're actually lucky because they stop wearing, but it really doesn't matter. By the time you clean them up, they just generally have to be rebushed. So, and you can see that arbor that was replaced as well. Now, the kind of almost last step in this whole process is replacing the phenolic plates. Now, as I said, this is where all these trains are basically bushed, or this is where the bearings are for these plates. They don't use the brass. They use this phenolic material as the bearing material. And I think they had a couple of reasons for doing that. One, they realized that with the motion going on in this train and the friction, it wasn't going to take long to wear the brass right out. The phenolic material tends to be self-lubricating to some extent. And they recognized that by creating a set of holes and other features in these plates, that they could turn them into oil wells as well and keep the oil in there and let it leach slowly out into the bearings as it evaporated or dried or whatever else. So that was the general idea. And it worked pretty well because some of these things you get, they'll actually still run, albeit they are a bit worn. So how are we going to make these things? Well, this is what we're going to do. First thing we're going to do is we're going to get the old ones out. So how do we do that? Well, we just laid this thing on, again, an anvil of some sort, whatever form you want, that has holes in it, and pick a hole that's as close as possible to a clearance hole. It has to be bigger, not smaller, but bigger than the head of the rivet. The rivet's on the other side of this thing. And I go ahead and I just take a punch and I knock out the rivet with that punch. And after I've done that 3 times for 3 rivets, this whole assembly is loose. So now I take that that phenolic plate and I draw it out. Literally, I just laid it on there and just traced it out and cut the shape. I basically cut the shape out on a scrolling saw. And the important part here is the location of these holes is super critical. You've got to hit these to be exactly like the original. Well, that's not hard. What you do is you start by drilling a pilot hole, and then you either file or start drilling the hole bigger until you are absolutely certain you are hitting that outline. And how do you know you're hitting the outline of the original part? Well, one really good way is you lay it on there, and if you can pass 440 nuts and bolts clear through it and the brass cover piece, then you're there. And so that's what you work towards. You work towards getting those holes located so you can make this little sandwich I'm showing you right here. Then, and this is the cool part, you need to locate the center of these holes. Well, the center of these holes, I'm here to tell you, is the center of these larger holes that are clearances in the brass parts. So how do you find the centers now? Well, you just turn up a bush that'll fit inside of that hole and inside of the brass hole, the larger brass hole. And while it's in the lathe and you're turning it, you drill it to the size of the hole that you're going to want to eventually drill through that plate. You fit it in and you go ahead and put it on the mill or the drill press even, and you run the drill through using this bushing as a template. And boom, you got your center. And you do the same thing for all these. You could actually use one bush here, start out at 052, and then once you've got that hole centered up and drilled, you go to put it back in the lathe, put the bush back in the lathe, turn it up to 073, drop it in here, and poof, you're done in a matter of no time making these holes. And you'll never find a better way to hit center on these things. They'll be exactly where they have to be, and they need to be in the right place, or your wheels are going to have problems working with each other, engaging with each other. And that's pretty much the key to this whole thing. That's what you do. And then you put it back together again. You can see the nice new plate. You make up rivets. The rivets are easy. Oh, by the way, I didn't mention these non-critical oil wick holes, as I call them. Yeah, what I did was I just went back and used this original part as a template to re-drill these holes. You can't use the original part as a template to drill your pivot holes because the pivot holes are worn. You don't know where the right location is anymore, but you can sure use the brass cover plate as a locator. But okay, so now you've got those drilled, and you come in here, you make 3 rivets on the lathe out of 260 or 360 brass, whatever you happen to have, and 187 head, 032 thick, round them off. And then the 108 is critical dimension. That's the size of the diameter of the rivet. And then the lengths differ in the clock. There's a couple of them are the same lengths, but then there's this top one that actually is on the rear plate that is a different depth. And the way you find the depth is you take this thing, this new plate, your brass and the plate itself, and just mic it with your calipers, determine the total width that you have to clear, and then you add 20 thousandths to it in order to be able to give yourself some material to rivet. And that's the hardest part. And you go ahead and you lay the rivet the thing. You lay the head on top of what I did here is I took a steel block and I just put a piece of aluminum behind it so that I wouldn't mar up my nice rivet. And I just took a round staking punch. Round head staking punch that's a little bigger than the diameter of the rivet, and give it a lightest tap, and it spreads the metal. Once the metal's spread, you can gently hit it with a flat punch and spread it out so that it clears all the wheels in the train. And that's not hard to do because there's pretty good clearance for the most part. And now you've got everything riveted back together, and you're ready to go to the next steps. Now, obviously, there are also some brass plate bushings, but there's not many of them. There's like 3 in the whole clock, I think, maybe 4. I don't know, but not many. And some of them do wear. The main wheel, both sides on this thing wore very severely, and both of those had to be rebushed. Don't forget to file back to center first. I make my own bushings, and I encourage folks to do that because I don't think you'd ever find a bushing in your kit that will be able to accommodate a 38 thousandths thick plate. So, and that's getting there. That's pretty much the deal here. But there's a couple of other things that come up with these clocks that are a good idea to address. One is the secondhand fit. This is the best time to deal with a secondhand fit issue. Because the last thing you want to do is find out you have to go and you have to put a die on a secondhand shaft after the movement's assembled. That is an ugly situation. So what I did here was I just, retapped both the shaft and made a new bushing for the second hand. These things were just a slop fit. They didn't even stay together. I don't know whether he had super glue on there or what before, but there was no fit at all. So made a new bushing, 1-72 thread. It came out great, and it'll never be a problem again in the life of the clock. So, all right. The other issue that I ran across with this particular clock was the setter shaft didn't have any anything left of it. I'm not sure why. So we ended up actually in this case ended up having to make a new shaft, and then we threaded. It's not shown here, but then it was threaded with a 348 left-hand thread, and then ended up having to make a new setter knob for it too, which also had obviously a 348. 348 I find is a really common thread size for setter shafts across a whole lot of different clocks. So it's good to have 348 right hand and left hand in your box of magic tricks. And then the other thing with these clocks is always check the fit of the minute hand shaft nut. It's a problem sometimes, and often there's issues with the nuts being stripped. And if you have to make a new nut or procure a new nut or whatever, now's the time to figure that out, not after the clock is reassembled. Because again, that's for the same reasons as with the second hand shaft. That could cause you no end of grief having to do machining on a clock that's all assembled. So although I must say that the motion works on this clock is really simple to take apart. Not much disassembly to do, but nonetheless, it's a good idea. It's good practice to take care of these issues during this stage. All right, so we're going to reassemble now. And so the first thing you want to do in the reassembly process is put the field and coil assembly back in. And what I do to set up the field and coil assembly is I use about a millimeter gap around this thing. It may not look like it here, but this is a pretty exploded view, kind of close up here. So, but try to set it. And what you'll notice, of course, now we didn't talk about this much, is there are two separate rotors. We talked about that, and one thing that doesn't come across clear in here, but is the case, is there's another rotor below this. And there's teeth. Unlike this section of the field assembly, which is smooth, the other layer below it has teeth on it. And those teeth align with the rotor, as we said earlier, so that you can, create that synchronism to the line. So if you've got these two and you want to make sure that the clearance is about a millimeter between both here and the one below it. And usually if you hit this one, the bottom one will be in line too, but check anyway, because you never know. You may have some assembly that's a little bit out of its geometry's off a little bit, and you'll want to get as close as you can to having equal clearance all the way around that entire rotor on both the upper and the lower rotors. So once you got that set, then you go ahead and you put the two wheels. Now, notice that, as I said, this is a real hard assembly, isn't it? Two wheels, not bad. But don't forget the starter shaft. It's an easy thing to forget, and there's a little spring behind it too. So always remember to do that. Oh, by the way, in doing your coil field assembly, there's two lengths of screws. The long screws go by the coil. That's the same reason as because the same situation we had before with the spacers that are under there. You got a little bit of a thicker geometry on this part of the assembly, so the screws got to be longer, here shorter. Okay, so that takes care of getting the backside reassembled. And we'll put the plates on now and move on to flip the whole thing over and go ahead and assemble your 1, 2, 3, 4 wheels on this side. That really is it. That's pretty much all there is on this thing. And then you'll don't forget your spring behind this center shaft and washer. And then you'll put the plate on here, this plate, and attach the nuts, and then put the motion works in and the 3 screws on that little top plate that you saw us take off earlier. And Then we go back, we turn it back over, and we install the flywheel and spring. Now this is a press, this flywheel, the way this thing is set up is this is a large, this flywheel, I'll call it a flywheel. I guess I don't have a better name. This rotor, for lack of a better name, or extension of the rotor, it acts like a flywheel. And it gives you, we talked about this a while back with the Hammond rotors, where there has to be somewhat of a loose connection between the flywheel and the rotor itself that ties to the line, because that is not a smooth action. And we want to use this to smooth it out and yet give it a little bit of angular inertia so that it can carry the rotor from one pole to the next, but not tied to it so tightly that this has the problem of vibrating with the line. Instead, it's loosely tied here. As you can see, this is a little piece of 12 thousandths piano wire that runs across here. And it often gets lost, and these clocks have real funny problems when that isn't there, because you don't have the flywheel action to carry it from one pole to the next. So if you lose this, get some 12 thousandths piano wire off of Amazon and cut to the length you see here and fit it in there. Now, this is this little piece here, this little bushing here with the slot in it is what fits onto the shaft. And it doesn't fit tight onto that shaft. But it has to fit tight enough so that there's no motion between that arbor and this little bushing. There has to be at least a reasonable amount of friction to hold it there. So if it's just sloppy loose, you might want to consider tightening it up, either with a round punch, or goodness help us if you have to use some sort of a sealant or sleeve retainer. It would be a good choice too, but sparingly on the sleeve retainer. You don't want it getting into the bearings. So there you have it. And over here, this is what's called the paddle. What this does, and you can see it's spring loaded, and we'll see it, you can see it in another view here on the left bottom. This paddle, what it does is, as this flywheel is rotating, and this is primarily for the backup power supply here when the power fails and the spring takes over. This acts as a governor. So this is a little counterweight here. We'll see. I have another picture of this, and the tension can be set so that if this tries to spin too fast, the edge of this spring, this is a small brass weight, and the centrifugal force pushes this out and it bangs against this paddle and slows it down. Yeah, it's a little crude, but it works. And it works very well. It's a very simple mechanism. So, and it does a reasonable job of regulating the time, as there's not that much normal clearance here. When this thing is spinning is about 20 thousandths. It's very little. So it doesn't take much motion and much error, much speed error to cause this thing to interact. So to reassemble this is a piece of cake. It looks like it's a mess, but it's not. This paddle is dropped in, the spring is threaded through it, and it's hooked onto the paddle here and hooked onto the plate here. It's real easy to reassemble it. So as long as you know how. So as far as adjustments are concerned, well, we just talked about one, which was the 1 millimeter clearance around the rotors. And the other is the speed. Now, clockwise makes it go faster because what it does is it increases the tension on the spring and it requires more centrifugal action to get this thing to hit the paddle. Counterclockwise will slow it down for the opposite reason. Generally, you don't have to touch these. Unless somebody's been mangling with it, it's probably pretty close and it'll work fine for you. So, I mean, it may just need to be cleaned up and put back on and it'll be okay. Now, I've gotten some of these things in where it's obvious somebody wanted to really learn about it because they were in there and the screws are stripped and there's a little brass retainer around the screw that kind of works on the flats of the screw to hold it in place. And those are usually all broken off and on it goes. But normally you'll find these things are not touched and they're good enough the way they are and they'll run just fine. So, but just be aware of the adjustment and that it is there. So here's our completed clock, working great, keeping great time. I was asked about the cords. Where do I buy cords? Well, I really like replacing the original cloth-covered cords with cloth-covered cords. The clock just looks better. It's more authentic. There's nothing I think worse than seeing a vinyl cord come off of a 1930 clock, where not sure that I can say that they had the materials to manufacture those cords at the time the way they do in what we call today zip cord style. In any case, the rayon cover mimics the exact look of the originals. And there's an interesting site. It sounds weird, but I buy a lot of stuff from these guys, 1000bulbs.com. They have a great selection of bulbs for your shop. They have cords, they have switches, they have all kinds of stuff for rejuvenating vintage electrical fixtures and supplies. So check them out. You can get these cords that I know of, gold, brown, black. There may be other colors I'm not aware of, but those are the three that are most common in doing restorations of these electric clocks. And I kind of think that's about where we are. Anybody have any questions?
Ken, how do you let down the tension on the spring?
Well, assuming that there's no way to go in there and do it in the conventional fashion. So what you got to do is, assuming that the wheels are free enough, just let the thing run itself out. Now, if the wheels are frozen together, oh boy, then what you have to do is you have to find a way to wire those two wheels together, the upper and lower wheels in that mainspring assembly, and then disassemble the thing and then let it down once you get it out of the clock. Because, I mean, you'll know it because you'll feel the tension on that spring, even though the tension doesn't manifest itself coming out the other end of the gear train because the wheels are seized up. So that's really all you can do is just kind of try to get wire wrapped around it so that you could take that assembly apart without that thing flying out of there for you. And then once it's out, you can unravel it.
Ken,
Yes.
why all the phenolic to begin with? Was it a noise reduction thing?
The original idea behind using it in the fiber wheels, yes, exactly, because it tends to be a little quieter at the speeds at which these rotors operate. Otherwise, you'd hear a grinding or grumbling sound, and it would kind of get annoying. And the idea was the fiber would dampen that a little bit, and it does a good job. I mean, the clocks tend to run very quiet. Now, when you look at it in the bearing plates, I think their idea there was that resin material was a very good self-lubricating kind of material. The other advantage that it has is where, for example, if you have a piece of the steel arbor kind of shave itself off and embed itself in brass, it tends to be a really, really effective cutting tool. Whereas with the plastics, they tend to embed, and it turns out that they don't do anywhere near as much damage to the arbor because, the material kind of embeds further into the plastic than it does into the steel, and so it does a lot less damage. But I think the self-lubricating was one of the key ideas behind making those plates out of that material.
Thank you, Ken. I'm going to check out. So enjoyed the presentation. Thank you.
Thank you for attending. We appreciate it. Anyone else have any questions?
Looking at eBay for these to serve as raw material for a restoration, there were a couple that were marked 50 cycle.
Yeah, and as most of you may have found out at some point or another, North America is kind of unique in that we run our mains supply on 60 hertz. Outside of North America, pretty much the rest of the world is 50. Now there's exceptions, and one of the most amusing is that Japan, half of Japan is 50 hertz, and the other half is 60 hertz. But I guess when you think about it, that wasn't that bad because back in the day, California used to be much the same way. Parts of California were 50 and parts were 60. And my suspicion, Dick, is that that's where you ended up with 50 hertz clocks. And, you know, the thing we have to be aware of though is that it may very well be that those clocks have been since converted to 60 hertz. As I was talking to some of my friends over in the Western Electrics chapter 133, who informed me that there were many clocks that were actually converted, but never the markings changed. So we don't know the history of those clocks. We can certainly find out easy enough, but you know, after the fact, of course, after they're in your hands, of course, you know, I make a converter so you can use them on whatever frequency you want, but that's a whole nother story.
Thanks.
It's only related because the same name, but I wonder if you've ever seen one of the Hammond bridge table automatic card dealing machines.
Are you sure it's a different company?
No, it's not a different company. It's the same company. It's Hammond.
Yeah. I think Lauren dabbled in quite a few different ventures over the course of time, and that may very well have been one of them.
Yeah, past president of NAWCC, David Morgan, brought one of these bridge tables to one of our meetings one time, and it was the damnedest thing you ever saw in your entire life. You just load a deck of cards in there, and it would automatically deal out 4 hands.
Wow.
Without any human intervention other than loading the cards in.
That's pretty crazy. And it was probably 100 years old too, to boot.
It was very old, and it was very scary to watch it because there are all these arms and levers and whatnot.
Yeah. Kind of akin to these clocks.
Yeah.
Anyone else? Thoughts? Other questions? Anyone have any of these clocks? How many people have one of these things? I think, Dick, you have a few.
I have one.
I think at last count, I had 4. But they don't all work, to be honest with you. I just haven't had the time to get them all going. Hope to someday. They're great clocks.
Well, it looks like an awful lot of work to restore one. I mean, you said starting out it was pretty easy, but it looks quite complicated to somebody new in the business.
Yeah, no, you definitely don't want this to be one of your newer projects. I think the complicated part is making the replacement components, assembling and disassembling these things and cleaning them up. I mean, it's not hard at all. I mean, I think anybody at any level could disassemble and reassemble the thing. You just got to be careful with the electricity part. Once you start to you find that you have broken teeth and worn plates, then things get a little bit more difficult.
If you have to move your family into
And who are the typical people? Are they collectors that bring these clocks to you, or are they someone that's got an old family heirloom they want to keep? And what do you usually charge for bringing it back into service ability with the repair?
It varies a lot because it depends on what exactly is going on. I mean, an extreme one can be well over, well over $500
You add an auto policy onto in this company where your homeowner's policy is, they may consider.
The simpler ones will be less. I mean, I've had customers say, I don't have a budget for more than X. And then you try to find a way to accommodate that. And you usually grit your teeth a little because you're putting worn materials back together again. But, you know, to do everything, I mean, it could get pretty sizable because it's a lot of time. It's just lots, as you can see, it's just lots and lots of time. And you know, the more you do, the better you get at it. But then if you don't see any for a while, you kind of have to relearn some things. And it's back to taking you a good amount of time again.
For recent Greenfield's signature, a path of destruction for Iowa jobs, leaving a company she helped leave $29 million in debt and unemployed Iowans in her wake. And Greenfield.
Okay. Well, I mean, if that's it, if there's no other questions, then we can adjourn. Feel free to email me if you have if you do think of other questions later, or you want to chat about a project you've got, always happy to engage you on it. So,
Ken, will you put this on the website?
yes, yes. We will definitely get this thing packaged up, and maybe Tim could help us with it. And if he feels it's reasonable, and then we'll put it up on the YouTube channel as well that we have.
The PDFs, will they be on the website?
Yeah, I can put them up on my website. I can also put them up on the Chapter 21 website as well. I don't know if we have a place reserved for it yet. I'll have to talk to our to Randy and David and see what we can do there. I don't know if you guys are on, if you know if there's a place on our website today where we put these, but happy to do it. It's not hard to post them up. Just got to know where.
Great
I'm not sure if
presentation.
Randy's
Thanks.
still on.
All right, guys. Well, appreciate your attending and your keen interest, and we'll talk to you again.
Thanks so much, Ken. That was great.
All right. Thank you, guys. Take care.
Bye for now.
Yes, we'll talk to you later.